Inside an Iranian mountain, thousands of machines are spinning at 50,000 RPM right now as you watch this. What's coming out of those machines is the exact material that sits inside every American warhead, and nobody, not international watchdogs, not the Pentagon, knows exactly how much Iran already has. For 20 years, Western governments have tried to stop this program, but the centrifuges are still spinning and time is running out. The question now is, how close are they, right now, to the bomb? Iran's first ever nuke would start its life here, 350 kilometers southeast of Tehran, in a patch of desert called Saghand. A drill bit the size of a coffee table is cutting straight down through bedrock. No operator sits anywhere near it. The control trailer is 50 meters back, and the man inside watches a grainy feed of the borehole on a monitor. His facility pulls around 40 tons of raw uranium out of this ground every year. Today's shift adds a few hundred more kilos to the pile. Here's how the rock gets out. The pilot drill punches a narrow hole straight down into the ore body, hundreds of meters deep. Afterwards, a reamer, a massive drill bit designed to widen a bore, gets hauled back up through that hole, chewing the walls wider as it rises. Next, the broken ore falls into a collection chamber dug beneath the deposit. Then a remotely operated bulldozer, with no driver anywhere near it, shoves the rubble onto conveyors that carry it up to the surface. Think of it like coring an apple from the bottom up, except the apple is radioactive and the core weighs 6 tons. And why don't any human hands go near that rock? Fresh uranium ore kicks up alpha emitter dust. Alpha particles barely scratch skin, but breathe them in and they lodge against lung tissue and sit there emitting radiation for decades. Miners working the face without sealed breathing gear develop cancer rates that don't show up on any actuarial table, so Iran doesn't send them. The whole operation runs on autopilot. A second mine at Cain near the port city of Bandar Abbas runs the same way. Here's the catch with that rock. Iranian ore runs between 0.1 and 0.5% uranium by weight, which means for every ton of rubble pulled out of Saghand, you get about a kilogram of actual uranium metal. And 99.3% of that kilogram is a slightly radioactive paperweight. Only one atom in 140 is the atom that matters. Uranium-235, the single isotope that sustains a nuclear chain reaction. The rest is U-238, useful for almost nothing you'd want to build a bomb with. Submarine ballast, armor-piercing tank rounds, but not weapons. What Iran needs is the other 0.7%, and getting it out requires a machine so difficult to build, so tightly sanctioned, that Iran was never supposed to have one. Yet, they have thousands. Walk into a Natanz enrichment hall. The first thing that hits you is the hum. Thousands of machines stand in perfect rows under fluorescent lights, each one a sealed metal tube about 2 meters tall and roughly the diameter of a dinner plate bolted to the concrete floor. They all vibrate. A technician in coveralls moves between the rows with a tablet, stopping every few machines to check pressure readings. He's inspecting one centrifuge every 30 seconds. There are 10,000 centrifuges in the facility. Inside each tube, a rotor is spinning at exactly 50,000 revolutions per minute. At the outer wall, the tip is moving around 280 meters per second. Not quite the speed of sound, but fast enough that centrifugal force can tear heavy atoms away from the light ones. Uranium hexafluoride gas, UF6, feeds into the bottom of the tube through a narrow pipe. Centrifugal force does the sorting. Heavier U-238 molecules fling outward against the rotor wall. The lighter U-235 molecules drift toward the center. A scoop at the top pulls enriched gas out. A scoop at the bottom pulls the depleted gas the other way. One pass through one machine and the enrichment ratio barely moves, a fraction of a percent. Which is why that technician isn't walking past 10 centrifuges. He's walking past 10,000. That UF6 comes from yellowcake. Iran crushes raw ore, runs it through a chemical conversion plant, and heats the output past 56 degrees Celsius. Past that, roughly the temperature of a hot car dashboard in July, the powder turns to gas. The machines link up in series. The slightly enriched output of one feeds the input of the next, each pass concentrating U-235 a little more. That's a cascade. Run dozens of cascades in parallel and you've got an enrichment hall. Iran operates an estimated 10,000 to 20,000 machines across multiple facilities, and the number keeps climbing. The original machines, the IR-1s, were based on 1970s European designs and broke constantly. Iran's newer IR-4 and IR-6 machines are a completely different animal. Sanctions actually made them better. When Iran couldn't import miraging steel, the ultra-high-strength alloy the West uses for rotors, engineers in Tehran designed the IR-4 with an all-carbon fiber rotor instead. 2 carbon fiber tubes connected by a carbon fiber bellows. Tell an engineer she can't have bricks, and she'll invent a way to build with something stronger. The IR-6 pushes further. Tip speeds past the sound barrier and roughly 10 times the capacity of the old IR-1. Sanctions didn't stop the engineering. They redirected it. Now look at the readout on the technician's tablet. The display shows one number that matters: enrichment percentage at the top of the cascade. Natural uranium starts at 0.7. Civilian reactor fuel runs at 3 to 5. The old nuclear deal capped Iran at 3.67. That display reads 60. And the math of that number scares every arms control analyst on the planet. Getting from 0.7 up to 20 burns about 90% of the total effort. Nearly every spin of every cascade goes toward that first climb. The final sprint from 20 up to 90, weapons grade, is fast. By then, the hard work is done. The last mile up the mountain takes a fraction of what the first climb did. Iran sitting at 60 means the mountain is already behind them. The last count from the IAEA, the United Nations nuclear watchdog, put Iran's 60% stockpile at 440.9 kilograms in September 2025. Raw material for roughly 9 nuclear weapons, if processed the rest of the way. The final push from 60 to 90 would take about 3 weeks running Fordow's cascades alone. Running Fordow and Natanz in parallel cuts that to days. Read that again. Iran has 9 weapons of material sitting in canisters right now, and the only thing between that stockpile and weapons grade is a political decision and a few weeks of spin time. Which raises the question that drove American intelligence insane for 2 decades. How did the country under total sanctions get 10,000 centrifuge? Every bolt, every rotor, every frequency converter, banned from export to Tehran under international agreement. Iran wasn't supposed to have a single machine. The answer starts with a stack of blueprints and a Pakistani metallurgist named Abdul Qadir Khan. In the 1970s, Khan worked at Urenco, a European enrichment outfit headquartered in the Netherlands, where he had clearance to the most classified centrifuge designs on the continent. He memorized them, photographed them, and walked out. Back in Pakistan, he used those stolen designs to build his country's first nuclear bomb. Pakistan detonated it in 1998. Then he did something worse. He went into business for himself. By the mid-1980s, Khan had built a smuggling network spanning 3 continents structured in 5 layers. Layer 1, money. Shell companies in Dubai handled the financing, with wire transfers routed through legitimate-looking import-export fronts, the kind of small trading companies that move a few $1 million a year and never show up on any watch list. Layer 2, logistics. A Sri Lankan businessman named BSA Tahir coordinated shipments from his Dubai office, and Tahir knew which freight forwarders asked questions and which ones didn't. Layer 3, manufacturing. A Malaysian company called Skami Precision produced the actual parts, labeled on paperwork as industrial vacuum equipment bound for legitimate buyers. Layer 4, know-how. Calibrating and assembling the components took engineering skill Iran didn't fully have in country, so the network imported it. German and Swiss engineers, including a man named Gotthard Lurch. Layer 5, delivery. Everything eventually arrived at a nondescript Tehran front company called Calais Electric. From the outside, it looked like an industrial electrical manufacturer. Inside, Iranian engineers were assembling centrifuges from Pakistani blueprints. Think of it as an Amazon for nuclear weapons, routed through 4 countries, so no single transaction looks like what it actually is. Between 1989 and 1995, Iran got its hands on more than 2,000 centrifuge parts through Khan's network, enough hardware to stock the first working enrichment halls Tehran would ever run. Not finished machines, parts. Rotor tubes, magnetic bearings, molecular pumps, frequency converters. A centrifuge shipped across a border is a nuclear proliferation event. A molecular pump labeled industrial vacuum equipment is just commerce moving through a free trade zone. The designs were called P1, Pakistan's first-generation centrifuge, itself a copy of the Dutch design Khan had stolen from Urenco. Later, Iran received more advanced P2 blueprints as well. And while this was happening, Iran chased every other path simultaneously. In 1992, Iranian agents approached the Ulba metallurgical plant in Kazakhstan and tried to buy enriched uranium directly, trying to skip the entire enrichment process and buy ready-made fissile material from the collapsing Soviet Union. That deal fell through, but it tells you how aggressively Iran was moving. Around 2000, Iran pivoted. They stopped buying parts and started building them. Engineers at Calais reverse-engineered the P1 design, identified the manufacturing tolerances, sourced domestic alternatives for the sanctioned materials, and began producing centrifuges entirely in-house. The blueprints had become factories. Then, in August 2002, the Western intelligence community nearly fell out of its chair. An Iranian dissident group held a press conference in Washington and announced a massive underground facility in central Iran. When IAEA inspectors finally got inside, they found a 100,000 square meter underground complex built for 50,000 centrifuges. Iran hadn't built a few prototypes in a garage. They had used Khan's blueprints as a template for an entire indigenous nuclear industry. The facility was called Natanz. Once the West knew it existed, there were two options: accept a nuclear Iran or find a way to destroy the program without starting a war. They chose option 3, a weapon that didn't officially exist. Inside Natanz, Iranian technicians noticed something they can't explain. Centrifuges are failing. Not one or two, hundreds. Rotors that should spin for years are blowing past their design limits and tearing themselves apart after weeks. But every time a technician glances at the control room monitor, the readings come back normal. Steady speed, stable pressure, no alarms. The monitors are lying. It takes months before Iranian engineers figure out the truth. The industrial computers running the Cascade hardware, Siemens-made boxes called programmable logic controllers, the same kind of equipment that runs factory machinery worldwide, have been compromised. A piece of malicious code is issuing commands the operators can't see. It's doing two things at once. First, it's telling the centrifuges to spin at destructive frequencies, surging past design limits, then dropping, then surging again. Over time, the oscillation tears the rotors apart from the inside. Second, it's recording 21 seconds of normal operation and looping those recordings back to the control room screens during the attack. The centrifuges are ripping themselves to pieces while the technicians watch a perfectly healthy facility on their monitors. Like watching a security camera footage of an empty room while someone robs it behind the screen. The worm is called Stuxnet, a joint American-Israeli operation codenamed Olympic Games. 4 separate zero-day exploits, software vulnerabilities the manufacturer didn't know existed, stolen digital certificates from legitimate Taiwanese technology companies to disguise the code as trusted software. The most sophisticated cyber weapon ever deployed, and the best malware analysts in the world needed months to reverse engineer what it was doing. The most remarkable detail isn't the software, it's how it got inside. Natanz was air-gapped, no internet connection, no external network access, built to be unreachable from the outside. So the CIA and Mossad, reportedly working through Dutch intelligence, recruited an engineer with legitimate access to the facility. That mole walked into one of the most heavily secured nuclear sites on Earth with an infected SUB flash drive in his pocket, the most advanced digital weapon in history delivered by hand. Stuxnet destroyed roughly 1,000 IR-1 centrifuges, about 20% of Iran's operational fleet at the time. Analysts figure it set the program back 2 to 3 years. Then the shadow war got less subtle. Between 2010 and 2012, Iran lost 4 senior centrifuge specialists in unexplained incidents. Stuxnet, the scientists, a June 2020 fire at Natanz that took out the above-ground centrifuge assembly hall, mysterious explosions at Parchin, and that facilities Iran never admitted existed. The shadow war cost Iran years of progress and its most irreplaceable minds, but it didn't stop the program. But it taught Iran 2 lessons. Any above-ground facility was a target. Any scientist working openly was next. The solution was obvious: go underground. Literally. A convoy of unmarked trucks rolls up to a checkpoint at the base of a mountain 20 kilometers north of the holy city of Qom. Guards in IRGC uniforms with radiation badges clipped to their chests wave the drivers through. The road cuts into the mountainside, past 3 separate security cordons, and disappears into a tunnel drilled straight through solid granite. Deep inside, behind blast doors, under 80 to 90 meters of rock, sits an enrichment facility Iran spent a decade hiding from the world. This is Fordow. Here's the math on the rock above it. 80 to 90 meters of solid granite, the equivalent of a 26-story building stacked directly on top of the centrifuge halls. To destroy a machine inside Fordow, a bomb has to punch through the equivalent of an office tower before it reaches the target. Fordow runs about 3,000 centrifuges, smaller than Natanz. But Fordow isn't about capacity. It's about surviving whatever Washington throws at it. The world found out about the place in September 2009 when American, British, and French intelligence services announced it simultaneously at the United Nations, and every analyst in Western capitals reacted the same way. Iran hadn't just hidden a facility. They buried it deep enough that no conventional weapon on the planet could reach it. Iran built Fordow specifically to eat the worst conventional strike the American arsenal could deliver. Then Iran kept building. After Stuxnet hit Natanz and the scientists stopped showing up to work, Iran hardened everything. New underground halls at Natanz, deeper than the originals. Centrifuge factories spread across multiple cities. They split research up. No single facility and no single scientist had the full picture. Destroy one node, and the network routed around it. Under the 2015 nuclear deal, the Joint Comprehensive Plan of Action, or JCPOA, Iran agreed to cap enrichment at 3.67%, reduce centrifuge counts, and convert Fordow into a civilian research site. Sanctions lifted in exchange. For a brief window, the engineering math worked in Washington's favor. Breakout time stretched from an estimated 2 to 3 months to a minimum of 12. Then in 2018, the United States withdrew. Iran got to work. They restarted enrichment at Fordow, installed IR-6 machines at Natanz, blew past 3.67, hit 20, hit 60. Breakout time collapsed from 12 months back to weeks. So the United States built the answer. A B-2 Spirit bomber banks over central Iran at 40,000 feet and opens its internal bay. A single weapons drop. 100 seconds later, on the ground below, a multi-story centrifuge assembly hall at Fordow disintegrates. Another one hits Natanz. A third one hits Isfahan. Buildings flatten. Tunnel entrances collapse. Craters open in the earth where above-ground facilities used to be. That was the GBU-57 massive ordnance penetrator, 20 feet long, 30,000 pounds, the weight of a fully loaded school bus, hardened nickel cobalt steel with a 5,300-pound warhead in the nose, engineered to drive 200 feet through reinforced concrete before the fuse triggers. The largest conventional bomb ever built, purpose-designed for Fordow and essentially nothing else. The only aircraft in the American inventory that can carry it, the B-2. The mission was called Operation Midnight Hammer. 7 B-2s flew a 37-hour round trip from Whiteman Air Force Base in Missouri and hit all 3 of Iran's primary nuclear sites in a single coordinated strike. Roughly a dozen GBU-57s plus Tomahawk cruise missiles from a Navy submarine in the Arabian Sea. Then the intelligence community split hard. Politicians in Washington declared the program obliterated. The analysts with access to the actual imagery were a lot more cautious. Some thought the buried halls took real damage. Others weren't so sure. Within weeks, IAEA monitoring picked up activity Iran hadn't disclosed. Commercial satellite imagery from June 9, 2025, 13 days before the strikes, caught something analysts didn't focus on until weeks after the fact. At the Natanz and Fordow sites, a convoy of flatbed trucks rolled out heading toward Isfahan. The trucks carried 18 large blue cylindrical containers. The containers were VPVR-M casks, sealed Russian-designed shipping cylinders built specifically to move highly enriched uranium between nuclear facilities, built to survive fire, impact, and keep radiation contained in transit. At maximum load, 18 of them hold up to 534 kilograms of 60% uranium. Iran's entire declared stockpile is 440.9 kilograms. You could move the whole thing in a single convoy. The timing tells the story. Iran quietly announced a brand new enrichment facility at Isfahan in June of 2025, a tunnel complex the IAEA had never visited and the United States apparently hadn't targeted. The convoy Iran ran the week before Operation Midnight Hammer likely hauled the most strategically valuable nuclear material on Earth into a site nobody was hitting. Those GBU-57s cratered empty buildings. Because of that, somewhere in Iran tonight, 18 blue cylinders are sitting in a room nobody outside Tehran has ever stepped inside, and nobody watching from above. Not the IAEA, not the Pentagon, not the satellites parked in geostationary orbit knows whether what's inside them is still 60% or whether it's already something worse. If you enjoyed this video, then watch this video on how uranium is made. Bye for now.